Hello everybody, glad to see you. Today we're going to talk about needed feature control frame for rotating components. As a first example, we are going to have this shaft assembly. As we can see here, at top left we are going to have a shaft, shaft coupling and shaft. We would like to talk about the needed feature control frame FCF for this shaft at the beginning. The same as always, as we know, we need to define datum references. The first item as we should consider, we need to know what is the length of that shaft. Is it long? Is it short? Do we have two bearings or one bearing, or we don't have any bearing? We need to know the contact area for that shaft. For example, for this shaft, as you can see here, we are going to have this contact area for bearing, and here this A, as we have defined it here for this example, it is contact area between this shaft and this shaft coupling. Now we know we have this possibility to define A here as a contact area between this shaft and this shaft coupling, and we can define B for the this section of the shaft, it is contact with the bearing. In the second step, we need to qualify these two axes. For now, we are going to qualify these two reference axes by using this TZ for the size. We are going to use H7 for axis A and also H7 for axis B. In this manner, we are going to qualify reference axes A and B. Here, as we can see for both of them, we have used E here. We have mentioned E here. E means envelope. As we can see in this example, for example, here this shaft has a diameter of 20 plus minus 0.1, an envelope. This E is going to represent, it's going to control the size of this shaft based on ISO standard. It's the maximum diameter of the shaft should not be more than 20.1 maximum material condition. Here I'm going to highlight or remind you what is the meaning of flatness. It doesn't control the orientation. In order to control the orientation of that, we need to have run out or total run out, or let's say perpendicularity. We will talk about that issue. At first step, we are going to have reference axes A and B. We are going to qualify A and B by the size tolerance, as we have used H7 here. And based on ISO standard, we need to write E here. But in ASME, if we don't write E, it is exactly the same as ISO standard. Let's see this example here. We are going to have a shaft, the diameter of 15.88 plus minus 0.13. As we can see here in this direction, the shaft diameter should be in this interval, 15.75 and 16.01 here. But the form should be in this interval, should not be more than 16.01. As it is mentioned, if we write based on ASME, it is exactly the same as ISO whenever we are going to write this E here, this envelope here. Now we have defined this D, these datum references. Let's talk about this end plate. We have location, orientation, and form. In order to control the form of that, we are going to use this flatness. As we have talked previously, flatness 0.1 is good enough. Let's say 0.05 is again acceptable, but if you are going to use 0.01, and we need to see what is the accuracy of this, let's say, shaft coupling and another shaft. These two surfaces should not see each other. That's why it is too tight here. We need to know the thermal load as well. What is the thermal load for that two shafts and let's say shaft coupling? After controlling the form, we need to know how we are going to control the orientation of this end plate. We can use total run out, we can use run out, we can use perpendicularity. Perpendicularity for this example is the same as this total run out. But total run out and run out, it is not the same as I have highlighted. It depends to the size tolerance for this lens. If it is too tight, we can use run out. If it is not that much tight, it is good to use total run out to control the orientation of this end plate. Yes, here we have another example. Here we are going to have a short rotating component. We are going to have reference plane C here, reference axis D here. For this end plate, in order to control the orientation of this end plate, as we can see, I'm going to show it by mouse. In order to control the orientation of this end plate, we are going to use total run out. It means this end plate should be in this interval 0.04. We are going to have two parallel surfaces perpendicular to D and parallel to C. We can see we are going to have reference plane, reference axis. We have used this total run out. We are going to have a common axis between A and B. Again, we can use total run out. That's why it is good to use total run out in comparison with perpendicularity. Somehow, I am going to highlight here, if we are going to have a plate, we can use, let's say, parallelism to control the orientation of that. Here we are going to have another example. In this rotating component, we are going to have reference axis C here. We are going to qualify it by having this cylindricity 0.005, and then we are going to have reference axis D here. Again, we are going to qualify it, this axis with cylindricity of 0.005. In order to control coaxiality between C and D, we are going to have this total run out. And then when we define this coaxiality between C and D, for the rest easily we can have this total run out respect to CD axis. However, for this hole here, we have reference D, and D is here, and D is D is we are going to have this total run out for D respect to CD axis. Somehow this whole axis is related to E in this example. Yes. Now we are going to have this shaft coupling here. We are going to have thread here. In order to control coaxiality of thread respect to AB axis, we are going to use this positioning control. We are going to have this diameter symbol here. For the threaded shaft, it is really good to write here major diameter. If we don't write this text here, if we need to type with this pitch diameter, it is very difficult. Somehow it is impossible. It is really good to write major diameter here to control the coaxiality of this threaded shaft respect to AB axis. At another end, we are going to have threaded hole, and for threaded hole it is good to write this minimum diameter to control the coaxiality of the axis of this threaded hole respect to AB axis with this TZ. Here, in this last page, I would like to highlight whenever we are going to use the run out, it should not, the TZ for that run out should not be less than the TZ for the size of that part of the component. It is the advantage of using run out in comparison with, for example, parallelism or perpendicularity. That's why here, again, it is good to use, let's say, total run out or run out in a set of, for example, perpendicularity. And how, however, this, it is good to keep in mind the TZ for run out is independent from the TZ of the size. Unlike parallelism. Here briefly we can see we are going to have, let's say, reference access A, B. We are going to qualify each of them. We need to define coaxiality between A and B. However, here we are going to have several feature control frame. In that manner, we are going to control the coaxiality between A and B. And for each end surface at left hand side and right hand side, we need to use one of these three. Here I have used, for example, let's say perpendicularity and flatness. I guess total roundout and flatness is really good. And for threaded shaft and threaded hole, we are going to use this positioning control with this diameter symbol to control the coaxiality of that. We haven't talked about these key slots. We need to use feature control frame to control these two key slots. For now, I would like to close this session. In coming session, again, I'm going to talk about this shaft and let's say tolerances and balance quality grade, and later on we will talk about this shaft coupling, and then we will talk about another shaft. Thank you for today. I hope you enjoyed. See you next time.